Hey, this is Yash, and this is my Physics 2212 Lab 4 presentation on circuits. So to get started, I'm going to give a little introduction. So the goals of this lab is 1, predict the behavior of circuits with resistors in series and parallel. Goal number 2, use multimeters to measure values of conventional current and potential differences in the circuits. And goal number 3, examine the behavior of ohmic resistors and capacitors, which you'll see later in the lab. Now for some key concepts. The first key concept is loop rule, which states that the sum of the voltages across a circuit will equal 0. The node rule, which equates to the sum of the currents will also equal 0. Ohm's law, which states that voltage equals current times resistance. And finally, the concept of resistors and capacitors in series and parallel. So if you see a diagram on the right, you can see how resistors in series and parallel affect the voltages, current, and resistance. We'll be focusing more on its effect on resistance than anything. Before a lab, we make some assumptions. So the first one being the resistance of the wire is negligible. The resistance of the emitter is also negligible for easiness calculations. And also the EMF, so the voltage of batteries, will equal the change of voltage of the capacitor plus the change of voltage of the resistors. Now for the experiment itself. For the system of the experiment is the ammeters and the voltmeters, which measure the current and potential difference along some points in the circuit. The surroundings is the circuit, which includes the wires, the electrical components, like the batteries, resistors, and capacitors. So part 1 of our experiment involved us using a two resistor slash ammeter circuit. So as you can see in the diagram on the left, the circuit consists of 2 ammeters, 2 resistors, one at 47 ohms, one at 100 ohms, and 2 batteries, each at 1.5 volts. In this case, we were asked to find the current at each resistor, which in this case is the 47 ohm and the 100 ohm resistor. The current. And the current in this case will be the same throughout the entire circuit because there's no junctions. So as you can see in the calculation in the bottom, we use loop rule, which means the sum of the voltages will equal 0. So it's 2 times the EMF minus current times the resistance of the 47 ohm resistor and minus the current times the resistance of the 100 ohm resistor, which in this case, the current equals 0.0204 amps. Now to find the voltages with each point on the circuit, the voltage between A and B is 3 volts because of the battery. The voltage between B and C is going to be 0 volts. The voltage between C and D, because of the resistor, will be negative 0.96 volts. D and E, 0. E and F, minus 2.04 because of the 100 ohm resistor. And then F, G, G, H, H, A, all 0 volts, because like we said, the resistance of an ammeter is negligible. As you can see, satisfies loop rule. Now part 2 is the ammeter in parallel to a resistor. In this case, we once again found the resistance of, the ammeter to be 0, like we said in the assumptions. And due to that, we found the current to be 0.0638 amps. And through other calculations, we found the actual resistance of the actual resistors and the resistance of the wire and ammeter, which are both 0. For the final part of the experiment, we dealt with an RC circuit, which doesn't deal with a battery, but rather a charged capacitor and a resistor. And the goal of this is to find the RC value, and the resistor in this case is a light bulb. So we're given a 9-volt battery to charge a 200 millifarad capacitor, followed by a 10 ohm resistor, which in this case is a light bulb, and a 20 ohm light bulb. Like I said, the values on the left side are not indicative of the values we actually used. Just want to make that clear. Now some data, the time of discharge was 8.62 seconds for a 10 ohm light bulb and 17.06 seconds for a 20 ohm light bulb. Now we calculate the resistance of a 20 ohm light bulb, which in theory is resistance times capacitance, so 20 times 0.002 equals 4 seconds. For the experimental RC, we use the sum of the voltage equals voltage initial plus e to the power of negative 2 of RC. We've isolated RC, and the delta of the voltages in the circuit was 7 volts, and the initial voltage was 9 volts. In this case, we found the RC value to be 3.98 seconds, so relatively close. Now for some analysis. So the source of the error, which for one thing was assuming an ammeter has 0 resistance, because in the real world it does not. 2 being faulty equipment, such as a connection between wires being worn down, or older voltmeters, ammeters that can't precisely track the values we're trying to find. Also, potential short circuits due to incorrectly attaching wires. Because we're not dealing with such high voltage, we're not gonna see sparks, but there's a chance that there could be a short circuit, which could affect the effectiveness of the equipment. Now, what if we simulate this experiment but use an ideal ammeter instead of a real one? What's different about an ideal ammeter and its effect on other components it's hooked up to? A real ammeter has resistance, like all electrical components, so assuming it has 0 resistance would lead to errors in calculation of current and resistance. With ideal, we can correctly assume its resistance to be 0. Thank you for watching.